Hey everyone, and welcome. Your SPM exams are on the horizon, so we're going to do a quick and powerful revision session on a topic you absolutely have to know: the states of matter. Let's lock these concepts in for good.
But hang on, before we jump in, just a quick tip. Watching this is a great start, but you know what's even better? Actually doing the questions. So after this, make sure you head over to www.mcqspm.com or just scan this QR code. You can also grab the MCQ SPM app from the Google Play Store. Trust me, it's the best way to make sure you really, truly get it.
All right, let's get into it. We're surrounded by stuff, right? But what actually is all this stuff? We're going to start at the very beginning. What is matter made of?
Okay, first things first, you're going to need a solid exam-ready definition. And it's pretty simple. Matter is anything that has mass and occupies space. Think about it. The water in your bottle, that's matter. The air you're breathing right now, also matter. But what about things like light or heat? Nope, those are forms of energy. It seems simple, but getting that distinction right is absolutely crucial.
So, what are the building blocks of all this matter? Well, it all comes down to these incredibly tiny particles. For your exam, there are three main types you've got to know. You've got your atoms, right? The basic units, like a single helium atom. Then you have molecules, which is when atoms team up, like in water or iodine. And finally, you have ions, which are just particles with a charge, like what you find in regular old table salt.
Now here's where it gets really cool. You take these same particles, atoms, molecules, whatever, and depending on how much energy they have and how they're arranged, they can act in completely different ways. And that, my friends, is what gives us the three states of matter. This diagram, it tells the whole story. Let's break it down. Take a look at arrangement number 3. See how everything is packed together, all neat and tidy? That's your solid. Now glance over at number 1, the liquid. The particles are still close, but it's more like a messy crowd. They can all slide past each other. And then there's number 2, the gas. Whoa, they're super far apart, just flying around like crazy.
Let's zoom in on the two big extremes: solid versus gas. In a solid, those particles are basically on lockdown. They're locked into this rigid structure, vibrating a little but not going anywhere. They have very low energy. But in a gas, they've busted out. They have tons of energy, zipping all over the place. The whole difference really boils down to two things: how much energy they have and how strong the forces are that are trying to hold them together.
So you have got to remember these key differences. Solids, tightly packed, they only vibrate, and the forces between them are super strong. Gases, they're far apart, move randomly, and the forces between them are really, really weak. Seriously, this table right here, it's exam gold. Burn this into your brain.
So the big question is, how do we get matter to go from, say, a solid to a liquid? Well, it all comes down to one thing: energy. If you add energy or take it away, usually in the form of heat, you can make these particles change their arrangement. We call that a phase change.
Okay, you've definitely seen this graph before. It's a heating curve, and it kind of tells a story. Up the side, you have temperature. Along the bottom, you have time. And what we're doing is adding heat steadily and just watching what happens to our substance, which starts as a solid.
Let's follow the line. That first slope, going up from P to Q, all we're doing is heating up the solid. The particles are absorbing that heat energy, and while they're still stuck in their spots, man, are they shaking. They're vibrating more and more like crazy. That movement is kinetic energy, and that's what a thermometer actually measures as temperature.
Now look closely at this flat part, the plateau from Q to R. This is the bit that everyone gets stuck on, but it's so important. We're still pumping in heat, right? But look, the temperature isn't going up. So where is all that energy going? Well, it's being used for a very specific job, breaking down the forces that are holding the particles together in that rigid solid structure. That process is called melting. And that constant temperature, that's the melting point.
And guess what? The whole process works in reverse too. A heating curve shows energy going in to melt a solid. A cooling curve, like this one on the right, shows energy being released as the liquid freezes and turns back into a solid. You still get that flat plateau, but this time it represents the freezing point.
All right, listen up, because here is a classic SPM favorite: sublimation. This is the special case where a solid just completely skips the liquid phase and turns straight into a gas. Energy still has to be absorbed for this to happen, and you have to know the key examples. Seriously. Iodine, naphthalene, that's what's in mothballs and why they seem to just disappear, and of course dry ice, which is just solid carbon dioxide.
Okay, last big concept for today. We have to talk about the fact that these particles are always moving. And this constant random movement, especially with gases and liquids, leads to a process we call diffusion.
This experiment is the absolute perfect picture of diffusion. So you've got a jar with this heavy brown-colored bromine gas at the bottom and plain old air at the top. If you just leave it alone, what happens? The random jiggling and moving of all those gas particles means the brown gas starts to spread out, moving from where it's crowded to where there's more space, until the whole jar is the same light brown color. That's diffusion in action.
So that leads to a really good question, right? If all gas particles are moving around randomly, do they all spread out at the same speed? And the answer is definitely not. And the reason why is actually super simple. Here's the golden rule. The lighter the particle is, the faster it can move. It's an inverse relationship. Just look at the table. Methane, with a teeny tiny molar mass of 16, zips around the fastest. But then look way down at sulfur dioxide. It's a heavy hitter at 64, so it moves way slower. Less mass equals more speed. It's as simple as that.
Okay, you've made it. We've covered the key ideas. Now it's time to put it all together and see what you've learned with a classic SPM-style question.
All right, take a good look at this table. We've got 4 different substances, P, Q, R, and S, and we've listed their melting points and their boiling points. Get ready to use this data. And here is your challenge. Which of these substances is going to be a liquid at a temperature of 50 degrees Celsius? Now, the trick is to remember what it means to be a liquid. The temperature has to be above the melting point but still below the boiling point. Okay? Hit pause right now. Seriously, give it a shot. You got an answer? The correct answer is P. And here's why. 50 degrees is way above its melting point of -17, so it's definitely not a solid anymore. But 50 degrees is still below its boiling point of 58, so it hasn't turned into a gas yet. It's in that sweet spot right in between, which means it has to be a liquid. And that is our deep dive into the states of matter. If you got that last question right, fantastic work. If you didn't, hey, don't even worry about it. That's exactly what practice is for. So scan this code, jump over to www.mcqspm.com, and do more questions just like that one. The more you practice, the more confident you'll feel on exam day. Good luck. You've got this.